In the next lecture, I will look at angular momentum of a rigid body, and in particular we will look at two examples. We will look at what is a spinning top and we will look at gyroscopes. So let's recapitulate. What is angular momentum? To understand what is angular momentum, we first need to look at what is the inertia matrix of a rigid body with respect to the mass center. So the mass center, remember, is located in a way such that the mass, so it is integral, RC is the integral of R into dV, volume integral, divided by the mass, total mass. And the moment of inertia is given by this integral AR square into rho dV. And what is AR? It is the skew symmetric form of this vector AR. And AR is the skew symmetric matrix for the position vector AR. So we had done this earlier. So this is the inertia matrix for this rigid body about the mass center with respect to this A coordinate system. This is a function of time, since A may rotate with some angular velocity, right? So in order to look at the inertia, it is better to compute the inertia in a body fixed coordinate system. So we have another coordinate system xb, yb, zb, which is fixed to the body. For the moment, it is located at the center of mass instantaneously at the same place. So now this AR vector can be written in terms of ABR. It's a rotation matrix of B with respect to A into BR. So the skew symmetric form of this vector AR can be written as ABR BR into ABR transpose. Okay, so this is just like any other matrix, how a tensor is transformed between two different coordinate systems A and B. So AR into AR, the two product of these two skew symmetric matrix, can be written as ABR into BR into BR into ABR transpose. So this is again skew symmetric matrix is converted from one coordinate system to another coordinate system. Okay, so the inertia matrix in A and B are related in this form. That the inertia matrix with respect to the A coordinate system is related to the inertia matrix in the B coordinate system pre-multiplied by this rotation matrix ABR and post-multiplied by ABR transpose. This we had seen earlier. Let's recap also a little bit about the angular velocity vector. So we had derived one angular velocity vector from the rotation matrix, which was r dot r transpose. So ABR dot ABR transpose. This we called as the omega r. Okay, this from here we could obtain a skew symmetric matrix AB omega r, and from that we could extract the angular velocity vector A omega b, and we said that this was the space fixed angular velocity vector. Similarly, we could also obtain a body fixed angular velocity vector from the skew symmetric matrix AB capital omega L. So basically, instead of R into R transpose equals identity, we started with R transpose into R is equal to identity. And we could obtain another skew symmetric matrix, which is ABR transpose ABR dot. And again, just like any other matrix or tensor, the left and the right skew symmetric matrices are related by means of rotation matrices. So AB omega R, ABR, AB omega L, ABR transpose. And the angular velocity vectors A omega b in the space fixed formulation. Okay, so A omega bs is nothing but A omega b in the body fixed reference system pre-multiplied by a rotation matrix. Okay, so this we had seen earlier. We had also seen that the angular momentum about the center of mass could be written in this form. So C is the center of mass, and with respect to some A coordinate system, it is the volume integral of this skew symmetric matrix AR into rho dV, and then this whole thing was multiplied by this A omega bs. So this quantity here, as I have shown in the last slide, it is nothing but the inertia matrix. So the angular momentum is nothing but the inertia matrix times this angular velocity vector. So this is a 3 by 3 matrix into 3 by 1. So we get a vector with 3 components here. So the derivative of the angular velocity matrix, okay, can be denoted by A HC dot. So this is nothing but the derivative of the right side. So we have d by dt of inertia matrix into angular velocity vector. So again A and S and B and all these things are consistent. Just to make it consistent, that we are multiplying vectors and matrices, and we are doing operations on vectors and matrices all in the same coordinate system. So now from that expression we can show that this AIC into A omega BS can be written in terms of ABR into BIC into ABR transpose. So AIC is this part here, and then A omega BS can be written as AB into A omega B in the body fixed angular velocity. So I'm just rewriting this in 3 terms here, and this angular velocity space fixed can be written in terms of body fixed. So now what you can see is this ABR transpose and ABR, they will give an identity matrix. Okay, so hence we are left with ABR IC into A omega B. So because these two will become identity. So the derivative of the angular momentum AHC, which is the derivative of the left hand side, is nothing but the derivative of these 3 terms, ABR BIC into A omega B. Okay. So if you again use chain rule, so the first term will be R dot into IC, okay, into A omega B plus ABR into the derivative of this is 0. Okay, so the last term is this into derivative of A omega B, so which is written here. So in the body fixed coordinate system, the inertia does not change. Okay, so if you are sitting on the body and you see these components of inertia, they are not changing with time. So hence the BIC dot derivative of this is 0. So now you pre-multiply both sides by BAR, so which is what? ABR transpose. So that this is the inverse of the rotation matrix. So if you pre-multiply by this, so again you can see this A and A will sort of cancel, and you will be left with this angular velocity derivative of the angular momentum in the B coordinate system, and the right hand side we'll have now ABR R transpose into ABR dot into this inertia matrix into A omega B, and then here we have ABAR into this ABR, which is ABR transpose into ABR. Okay, so this again becomes an identity matrix, and we'll have BI and A omega B derivative of that. Okay, so finally we can now see that this is the angular velocity, angular momentum in the B coordinate system. And what is this? This is R transpose R dot. So this is the left skew symmetric matrix into BI. Okay, and then we have this A omega B, which is here. And then these two becomes identities. So we have B into IC into A omega B dot. Okay, so derivative of the angular velocity vector, the body fixed angular velocity vector. So in vector form, this is the same as this, but this quantity can be written as BIC into A omega B dot. So this is the term coming here, and this quantity here, remember this is a skew symmetric matrix. So this is what, like omega cross I omega. So this part is I omega. Instead of taking a skew symmetric matrix, I can say this is like a cross product. So what do we have here? The derivative of the angular momentum in the B coordinate system is something like I into derivative of the angular velocity plus omega cross I omega. Okay, and this whole thing will be equal to the net external moment which is acting on the rigid body. So this is well known. So the linear momentum is change of linear momentum is equal to the external force. The change of angular momentum is equal to the external moment which is acting on the rigid body. This is the well-known Euler's equation. An interesting fact about Euler equation is that it need not be about the center of mass. The Euler equation also is valid or has a similar form if it is about a point O which is fixed in A. Okay, so I could have written BHC dot O, which is, but the point O has to be fixed in A. It need not be about the center of mass. So let's look at an example. This is an example of a free spinning top. So what we have here is a top which is spinning, and this point is fixed in the OA and OB are at the same place. So we have an XA, YA, ZA axis, and this top has a body fixed coordinate system which is ZB, which is along this direction as shown here. Then there is an XB and there is a YB. So there are these names for these different axes and the angles. So the rotation about Z axis, this θ1 is called precession. So if you have this top which is spinning, then it is also rotating about the ZA axis. There is also a tilt of this top about the XB axis. So this is Euler angles. This is about the moved x-axis. Okay, so this angle is θ2, and this is sometimes called nutation. It is also sometimes called tilt. And there is a last angle which is spin of this top, and that is about θ3. This is θ3 about the Z axis. So this is a classic example of Euler angles. So Z, X, Z Euler angles. Okay. So in this free spinning top, there are no external forces or moments which are acting. The symmetric top is a special case of general top, in which what happens is that Ixx of this inertia matrix of this top about xx, xs is, remember, integral of y square plus z square, is same as Iyy, and both of these are not equal to Izz. So Ixx, Iyy, Izz are the principal moments of inertia of this top about this xb, yb, zb. So now we can write the Euler equation, which is that B I, that inertia matrix with respect to the body fixed coordinate system, into A omega B dot. So this is like alpha, rate of derivative of the angular velocity vector, I into alpha plus omega cross I omega should be equal to the external moment. But we are looking at a free spinning top with no external forces or moment, hence this is equal to 0. So if you now expand this, so what is this? This is Ixx, Iyy, Izz. What is A omega B? It has components of omega x, omega y, omega z. So if you expand all this, you will get Ixx into omega x dot, because this is the derivative of the angular velocity, plus omega y into omega z into Izz minus Iyy equal to 0. So that is one equation. Likewise, we will get another equation which is Iyy into omega y dot plus omega z omega x ixx minus izz equal to 0. And the third component of this vector equation is izz into omega z plus omega x into omega y into iyy minus ixx equal to 0. So this is a symmetric top, so hence izz into omega z is 0. So you can see that iyy will be equal to ixx, so hence this term will go to 0. So izz into omega z is equal to 0. So which means what? Omega z is constant. And then if omega z is constant, we can see that omega x dot, okay, will be equal to minus some another constant capital omega into omega y, and omega y dot will be this capital omega into omega x, where this capital omega is izz minus ixx divided by ixx. Okay, so just by looking at these two equations and putting omega z as constant and then simplifying and noting that ixx and iyy are same. Okay, so what we get here is two differential equation. Omega x dot is something constant into omega y, and omega y dot is some constant into omega x. Okay, so both of these two equations, if you take another derivative of this and then substitute back what is omega y dot, you will get omega x double dot plus omega square capital omega square omega x equal to 0. Okay, you can see that. So this derivative is omega x double dot is minus capital omega omega y dot. So omega y dot is capital omega into omega x. So you can substitute here. So you'll get some omega square into omega x equal to 0. So this capital omega square is constant. Remember, omega z is constant, and this ixx and izz, these are known constants. So hence this omega x component is some a0 sine omega t plus phi. So this is the simple second order equation with omega square is positive. So hence the solution is some sine omega t plus phi. And omega y can be written as omega y is omega x dot divided by minus omega. So we will get another equation which looks like this, which is minus a0 cos omega t plus phi, whereas omega x is plus a0 sine omega t plus phi. Okay, so we can show what is happening to this small omega and what is actually capital omega. So basically, if you have izz greater than ixx, so this omega vector with components omega x, omega y, omega z is rotating at about this cone, okay, at some angle alpha. And if izz is greater than ixx, the direction is this way. If izz is less than ixx, the direction is this way. So since omega x square plus omega y square is a0 square is a constant and omega z is a constant, so this magnitude of omega is also a constant. Magnitude of omega is a0 square plus omega z square, it's also a constant. So basically what is happening geometrically, that this angular velocity vector omega precesses around this symmetric axis, the body z axis, at a rate capital omega, and it goes anti-clockwise if izz is greater than ixx, and it goes clockwise if izz is less than ixx. This is called oblate and this is called prolate. So the omega is in terms of the body fixed angular velocity vector. We can obtain omega using z, x, z Euler angles. Remember, z was first was precession, then it was tilt, and then it was spin for this top. So the angular velocity vector in terms of theta 1, theta 2 and theta 3 and their derivatives can be obtained in this form. This is the standard Z, XZ body fixed Euler angles. So we have theta 1 dot sine theta 2 sine theta 3 plus theta 2 dot cos theta 3, that is the x component, and the y component is theta 1 dot sine theta 2 cos theta 3 and minus theta 2 dot sine theta 3, and the z component is theta 3 dot plus theta 1 dot into cos theta 2. So the orientation in terms of the Euler angles theta 1, theta 2 and theta 3. So theta 1 is about z, theta 2 is the tilt, z is again the spin. We can obtain by integrating. So once we know what is the left hand side, we can integrate these three differential equations and find out what is theta 1, theta 2 and theta 3. So what have we done? That for this free spinning torque, we can solve the differential equations, and I can show you how the top is spinning and how it is precessing about the z-axis, and in that sense it is tilting, and everything can be solved in closed form. Okay, so this is one of those rare examples of a 3D case of something which is spinning and which we can obtain the orientation in closed form, because we know what is angular velocity from the previous slide, and then we can find out what is theta dots from this and theta by integration. When the external moment is present, so for example there is a weight of mass times gravity which is acting at the center of mass, then we cannot solve these equations. Nonlinear equations is not straightforward. However, a lot of people have worked on these tops, and there is something called as an elliptic function which I don't want to get into. I can find the solution when there is a mass mg which is acting at the center of this top, and then the solution is in terms of elliptic functions. Let's take another example. This is the example of a gyroscope. Okay, and we will look at what is called as a free gyroscope. So a gyroscope basically consists, there are many kinds of gyroscope. There is something which is called as a 3 gimbal configuration. So what is a gimbal? So the gimbal is this ring like thing. Okay, so there is a spinning disc which is mounted on this ring like thing, and this ring in this example is rotating, could rotate about the x-axis. Okay, so this gimbal itself can mounted on another outer gimbal, and then that outer gimbal can also rotate. Okay, so we could have some rotation of the disc about x-axis, and this gimbal can rotate about the y-axis by theta y dot, and then this outer gimbal can again rotate about theta z dot. Okay, so this is an example of a 2 gimbal configuration where you have an inner gimbal and an outer gimbal and a spinning rotor. So we'll come to that little later what it is used for. So basically, if you had a 3 gimbal configuration which is not shown here, these gimbals completely decouple the angular motion of the moving object from the rotating disc. So there is this whole thing is mounted, these hash lines are the moving object. So this is fixed on a, let's say a car or an airplane or a missile or something which is moving, and then inside this moving object we have all these rings or gimbals, and then finally there is a rotating disc. So as the object moves, theta y and theta z, so we could measure what is theta y and theta z, and it gives 2 Euler angles. Okay, so remember, you can see here it is about the rotating or moved y and z axis. The x axis is the spin axis. This x axis itself is rotating by this gimbal, so this rotating disc can tilt, and that is the rotation about y, and then this whole thing can rotate about the z. So if I could measure what is happening at these 2 rotations about y and z as the body moves, I can somehow figure out what are these 2 rotations. So these are the 2 Euler angles corresponding to the moving body. So if you have 2 free gyros, and they are mounted in a way such that one of them gives y and z, the other one will give some x and y. So I can find all the three Euler angles of this moving object. Okay, so basically what is happening is with two free spinning gyros, I can obtain what is the Euler angles or the rotation of this rigid body or this body on which these two gyros are mounted. There is of course this issue of some friction at these joints, at these rotary joints. So then due to friction there will be some drift. But nevertheless, conceptually, if I can measure what is the rotation about the y-axis and z-axis in this figure, and for another gyro rotation about x and let's say y, so together I have x, y and z, three rotations. So in this two gimbal configuration, the spinning rotor is about the x-axis. This is called as the spin axis. The inner gimbal can rotate about the y-axis, and the outer gimbal fixed to the moving object can rotate about the z-axis. We can also have a gyroscope where in the y-axis this motion is constrained by a spring or a damper. Okay, so this is a single gimbal configuration. These are called constrained gyroscopes. So basically this disc is spinning about the x-axis, but the motion about the y-axis, there is a spring K and a damper. Okay. So with a torsion spring resisting the motion about this y-axis, these are called rate gyros. So basically what we have is Ixx into omega z and omega s is equal to Ks into theta. So there is some theta rotation happening over the y-axis. There is a torsional spring. So Ks into theta will be equated to Ixx into omega spin and also omega z. So the spring constant is K, and from here we can see that theta is given by Ixx into omega s divided by K into omega z. So if I can measure what is this rotation, I can find out omega z because I know how much, at what speed this disc is spinning. That is driven by some motor. Okay, and if I know what is Ixx and if I know what is the spring constant, measuring theta will give me omega z. Okay, so measurement of an angle gives the angular velocity along the z-axis. So it is interesting to see that the angle is rotating about the y-axis, but it is measuring this omega z, which is the component about the z-axis. If you also have a damper which is resisting this motion about the y-axis, these are called rate integrating gyros, because then what will happen is this Ixx omega s omega z will be equal to b into theta dot. Here it was Ks into theta. Okay, so this is a b into theta dot. So basically what it means is delta theta will be equal to delta theta z. So I am assuming omega z is some delta theta z divided by delta t. Similarly here delta theta divided by delta t. So these two t's will go. So if you could measure this delta theta, I can find what is the integral of this omega z. This is delta theta z. That's why these are called rate integrating gyros. So here theta was proportional to the angular speed or component about the z-axis. Here the rotation or the change in rotation is proportional to the change in rotation about the z-axis. So again, if you have 3 rate gyros and 3 rate integrating gyros, we can obtain both the orientation and the angular velocity in 3D. So with 3 of these rate gyros, I can find omega x, omega y, omega z if I mount it correctly about the x, y and z axis. Similarly, if you have 3 of these, then I can find the orientation. So this is an interesting fact that with 3 rate gyros and 3 rate integrating gyros, we can find the orientation and angular velocity of the object on which these gyros are mounted in 3D. Finally, we have this 2 other kinds of gyros. These are called a control moment gyroscope. So this is a single gimbal. Okay, the spin axis is again about the z axis. So this is the disk which is rotating at some omega s constant speed. So if there is a torque about the y axis, okay, the reaction can be seen about the z axis and the other way around. So if there is a torque which is acting on this this body on which this gyroscope is mounted, so this is fixed to the moving object. If there is a torque about the z axis, then the reaction can be seen about the y axis. Okay, so what is the purpose of this? So if you spin this and if there is a torque which is acting here, then you can use this mechanism to change the orientation of the object. So you supply one torque here and it will rotate about the y axis. Likewise, you apply one torque about the y axis and this whole object will rotate about the z. So I can change the orientation of this object due to the torque which is acting in a different direction. You can also use these two what are called as anti-roll stabilization in boats. So assume that this is like a boat, okay, in which there is a spinning rotor and this rotor is spinning about the x-axis. Okay, so now if there is a torque which is acting about the y-axis, okay, this is sometimes called as a roll torque. This will be resisted by a reaction torque about the z-axis. Okay, similar to this idea here. So if you have a gyro which is mounted in this way, that this is rotating about this and the boat is going along the y direction. So if there is a roll, which means that the boat is rotating about the y axis, depending on how fast you are spinning, this motion, it will resist that motion. It will resist that roll motion. Okay, with that we will stop about this top and gyroscope. One last word. We want to sometimes measure what is the rotation of an object. So as I showed you, with 3 rate gyros and 3 rate integrating gyros, we can measure the rotation or orientation and the angular velocities. There are other ways to do it, and this slide shows there's something called as a MEMS gyroscope. Okay, so what is a MEMS gyroscope? We have a fixed body and inside this there is an inner frame, and inside this inner frame there is a mass which is going up and down. Okay, so this is the motion of this mass, and this mass is supported on springs in this way, and this inner frame is also supported on springs in this direction. So as you can see, let's call it x direction and this is y direction. So if this whole body is rotating about the z direction, which is coming out of the page, and then this mass is translating along this x direction, so z cross x will give me a force or a motion in the y direction. So this is 2 omega cross v relative. This is from the Coriolis acceleration. So omega is coming out, v relative is this. So omega cross v relative, this body will move left or right. Okay. So as it moves left and right, there are these fingers. Okay, so there is a one set of fingers which are fixed to the outside, and then there is another set of fingers which is on this inner frame. So what you can see is, because of this Coriolis component, these fingers will go, the moving fingers will go towards this fixed fingers. Okay, and these are charged in the sense that I can measure the capacitance between this finger and this finger. So what is happening? If I have a angular speed of this whole body, which is omega. Let's say it is along the z-axis. The v relative is along the x-axis. So there will be a motion about the y-axis, and then this distance between the fixed and the moving fingers will change, and we can measure the change in capacitance. So this change in capacitance after some calibration and so on can be shown to be proportional to this omega. Okay, so we are controlling this v relative. This we know by some drive mechanism. We can move this up and down, and then we measure the change in capacitance. Then we know what is omega. Okay, this is a way to measure the angular velocity about one direction, which is the z direction. And if I mount 3 such devices, in which case I can measure the 3 components. So if I mount one device such that this is vertically in this plane, then the other one is in the other plane, xz plane, and another one is in the yz plane, I can obtain the 3 components. Okay, this is what is called as a MEMS gyroscope. This is very different from what I showed you about this rotating spinning disc. These are very small and nowadays very accurate, and they can even fit into your mobile phone. So in your mobile phone you have gyroscopes, and you can also, I will show you later, we have accelerometers which can measure the motion of this mobile phone. Okay, we can get the acceleration and angular velocities of this body on which this is mounted. There are another very well-known way of measuring angular velocity and orientation. These are called fiber optic gyroscope. So basically what you have is a small fiber optic fiber in which you send through a light, and this goes round and round and it comes out into a detector. So now if this object is moving, which is subjected to some kind of an angular velocity, so the path traveled, okay, one light beam which is going like this and another light beam which is going in the opposite direction, there will be a phase difference which is introduced. If there is no angular velocity, the phase difference will be something. And if there is rotating, okay, this whole device, then there will be a phase difference. This is called as the Sagnac effect. Okay, so if you can measure the phase difference, we can find out what is the angular velocity of this object on which this fiber optic device is mounted. The same story is happening here. This is called as a ring laser gyroscope. Okay, so again we have a laser which is going in one direction like this, and there is another beam which is going in the opposite direction, and then this body is somehow rotating. Then this 2 laser beams will travel slightly different lengths. Okay, and if there are these mirrors placed, okay, so we can see that there is a frequency shift, okay, due to this arrangement, because due to this rotation. This is again based on the Sagnac effect. So we have some laser, one counterclockwise beam and one clockwise beam, and then this whole object is spinning. You can see some bit in this readout sensors, you will see some frequency shift happening. Okay, in one direction the frequency will be something, in the other direction the frequency will be something else. Okay, and again the frequency shift is related to the angular velocity of this object. So in summary, in this set of lectures, or in this lecture, we have looked at angular momentum, and then I showed you how this angular momentum and the rate of change of angular momentum can be related to the external moment, and we have this Euler's equation. And then I showed you what is a free spinning top, and this whole notion of a spinning top which is also precessing about an axis, and it could be tilting also. And then the similar ideas can be used, this angular momentum and so on, can be used to explain the principles of a gyroscope and its application. So a gyroscope can be used to measure the angular speed or the orientation, and it can also be used to change the orientation of a rigid body, which is often used in spacecraft, or it can be used to stop a rigid body like a boat to roll. Okay, and I showed you a little bit about how we can measure orientation and angular velocity using more modern techniques like MEMS or even a fiber optic device or a laser. So in summary, for this whole week, I have looked at what is mass and inertia of a rigid body. We have looked at external forces and moments acting on a rigid body. And then we have looked at the concept of generalized forces acting on a rigid body and in a multi-body system. We have looked at linear and angular momentum of a rigid body. And then we had looked at application of Euler equations, which is rate of change of angular momentum is equal to the external moment. And we had applied this for two kinds of examples. One is a free spinning top and a gyroscope. In the next week, we will look at equations of motion for a multi-body system. Thank you.